And then a third type of really roughly estimating probability is subjective probabilities. And this is where we're really doing a rough estimate based on knowledge of the relative circumstances. Which doesn't make a whole lot of sense until we look at an example, see what this actually means. So an example of the subjective probabilities approach, if someone says the probability of seeing a celebrity on the street on any given day is, about 1 in 10,000. I don't know. Well, obviously that's going to depend on where you are. But you could sort of, I guess you could sort of say, well, let's use a relative frequency approximation. How many days have I walked around on the Earth, and how many times have I actually observed encountering a celebrity? So maybe 1 in 10,000 is a little low, but that kind of data would be kind of hard to to tabulate. We're just doing an educated guess. It's unlikely. It's not as unlikely as me getting struck by lightning or winning the lottery. But it's definitely much more unlikely, or much less likely, than me, seeing somebody that I work with, on any given day. So it's just an educated guess. Now we can do that for certain things that maybe we actually could calculate. Example that's in the textbook is, the probability of dying in a plane crash is about 1 in 10 million. It's just somebody's, kind of rough estimated guess, because it's very unlikely to die in a plane crash. There's thousands and thousands of flights every day, and fatal plane crashes are pretty rare. Of course, we could actually calculate that. I mean, that data is available. If we wanted to research it and look it up and say, well, exactly how many flights have there been, and how many people were on those flights, and total that up and figure out how many people flew in a plane in the last 10 years, and then how many people actually died in plane crashes in the last 10 years. And we could actually compute the relative frequency approximation of that probability much more accurately than just making a wild estimated guess. But sometimes just an educated guess is sufficient for a casual conversation or something. So we have 3 approaches to probability. The classical approach, we're actually finding the exact probability of something occurring. Relative frequency, we're approximating it based on things we've observed, and then the subjective probability is really nothing more than an educated guess. Now, we're not going to do a whole lot with the subjective probabilities approach, but we will do quite a lot with the relative frequency approximation, because in statistics, the practice of statistics, often involves observing procedures and experiments and collecting data, and then we're calculating, summing up, adding up the number of times something happened, and we can compute relative frequency approximations, and those allow us to predict what we think the actual true probability is. And so we make use of what's something that's referred to as the law of large numbers. Which could mean all sorts of things, but what it means in the context of statistics is as a procedure is repeated more and more times. The observed relative frequency probability tends to approach the actual probability. For example, if we roll a six-sided die twice, or that's not if, let's just say, suppose we roll a six-sided die twice, 2 times. Suppose we roll a six-sided die 2 times and get a total of 5. Then we repeat the procedure, roll the six-sided die 2 times, and get an 8. And so on. We repeat it several times. Well, obviously, we calculated the classical approach to the probability. We calculated this probability as 1 in 18 that we're going to get a total of 3. Well, obviously, if I only roll a die 10 times, I'm not going to get a successful time 1/18 of the time if I only roll it 10 times. It's impossible to get it 1/18 of the time. Even if I roll this, do this procedure 18 times, I'm probably not going to get exactly 1/3. But if we repeat this procedure thousands of times, the relative frequency probability will be close. Well, we say should, because there's always the possibility that I could get 1,000 snake eyes in a row. 1, 1, 1, 1, 1, 1. It's extremely unlikely, but it should. That relative frequency probability should be close to the true Oh, I'm sorry. I never said we were going for probability of 3. We're trying to estimate probability of a total of 3. That's what we were doing before, but I should say that. That's what we're doing here. Trying to estimate the probability of getting a total of 3. If we repeat this thousands of times, the relative frequency probability should be close to the true probability, which we calculated before was 1 out of 18. Okay. Well, we can use that to predict. And we say, well, if I do this 1,000 times, I can take 1/18 of 1,000 and calculate how many totals of 3 I should get, roughly. Again, this isn't proving anything, but the more we do it, the more it should balance out, because I'm going to get, some may get a streak of low numbers or a streak of high numbers, but in the end, they should balance out to roughly 1 out of 18. Let's look at another example. This one is using a little simulator. And in this simulator, we're flipping a coin. And we know flipping a coin, if it's a fairly weighted coin, we've got 0.5, a 50-50% chance of getting heads and a 50% chance of getting tails. So we say the probability here is 0.5. And so we're going to simulate this. Not actually flipping a coin, but let's flip it one time. Okay, in this simulation, we see it over here, it was tails. So right now we got a 0. Our relative frequency is 0 out of 1, right? The proportion of heads was 0. We had 0 successful heads out of 1 observed event. Let's flip it one more time. Now I got a second tail, so right now I'm 0 out of 2. Flip it a third time, we got heads. Okay, so far I've observed 1 head out of 3 flips. So that relative frequency probability is 1 out of 3. Let's flip it up a few more times, and we see over here we're kind of tabulating this. Okay, that's a third tail, so now it's 1 out of 4. That's a second head, so now it's 2 heads out of 5. 2 out of 5.4. And we got a third head, so now it's 3 out of 6. Now it's finally 0.5. Okay, well, we'll just do a bunch more of these, and we see that as we go, every time we get a heads or tail, it jumps a little bit in this little chart. It goes, you know, that value of the proportion jumps up a little bit or goes down a little bit. You see, the jumps were much steeper, much more pronounced at the beginning than they are now, because now every time I add 1 to the numerator and the denominator, or just to the denominator, it's not going to change the value of this proportion, this fraction, as much as it did initially. And things are going to balance out. So right now we're more than 50%. You know, right now 53.57% of my tosses have been heads, 30 out of 56. But as we do more and more and more and more, it's going to settle. It's going to get closer and closer to 50%. Obviously, there's always a chance that I could flip this coin and get 1,000 heads in a row, which that's extremely unlikely. Let's jump ahead a little bit. Let's do like 10 tosses at a time. Right, and you'll see over here, it just does 10 more of them. We're well below 50% now. We were well above 50%. Now we're below. Let's do 1,000 flips. It's going to take it a little bit of time. But we see what's happening here is it keeps flipping them, and you know, it's staying above 50%, but it's not changing that much. Eventually it'll settle back down and get closer and closer there. So obviously this will take a while. We're not going to let it finish, but you get the idea there. Okay, pause the video and let it finish its simulation. So we now have, after 1,143, 582 heads, which is pretty close to 50%. Okay, the more we do, the closer this number should get to 50%. And so the larger our number of observations are, the more reliable our relative frequency estimation is. Of course, this is something we can check, because the classical approach to probability applies here, because we know that the probability of getting heads or tails are equally likely. We know each one is a probability of 50%, 0.5, of occurring, and so we can use classical approach to probability to actually calculate what the true probability is of getting heads on a toss of the coin. And then we did a simulation to observe relative frequency, and we see that yes, the law of large numbers does seem to be supported by what we've observed here. But obviously in a lot of other situations, the classical approach to probability doesn't apply, either because I'm looking at 2 or 3 or more outcomes that don't have the same probability of occurring, or it's not something that I can calculate because I don't know what those values are. So sometimes all we can do is do a relative frequency approximation. But this lets us know, this gives us some assurance that even if I am relying on a relative frequency approximation, if I've observed this basketball player attempt so many shots in a season, or whatever it is, I know that I can rely on that the more shots that basketball player takes, the more accurate that probability is. If the basketball player has only attempted 4 shots, then it's much more possible that maybe he just had a good night or a bad night. I can't necessarily rely on that. That he just, he took 3 shots. Maybe he happened to be going against a particularly good or bad, defensive player or something. We haven't observed enough data to get an accurate probability there. But after he's done hundreds or maybe thousands of shots, just like with this toss of the coin, it's not going to fluctuate that much. And so we'll get a pretty accurate estimation of what that player's probability is for every successive shot.